is one of a series of short videos showing how to do computational physics using MATLAB. In this video we're going to explore some of the matrix operations which are available within MATLAB. MATLAB, as the name might suggest, means matrix laboratory, and therefore, unlike some other programming languages, MATLAB has a tendency in its syntax to do matrix operations rather than doing what are more often used in programming, which are array operations. We'll see how that works in just a moment. But to begin with, let's define a matrix in MATLAB. So we start with our window in MATLAB as usual, and we go to the command window, and we'll define a matrix A, and we'll use our square bracket notation as usual, and we'll say 1 space 2 for the first row of our matrix, and we'll do 3 space 4 for our second row. And notice that there's a semicolon to divide the two rows from each other. When we press return, you'll see that A has now been defined as a matrix. Now you may wonder whether or not we need to have the commas, which you can see on the right hand side, and the short version of the answer to that question is no, it doesn't really matter. Let's try defining the matrix A again. Say A equals 1, 2, semicolon 3, 4, and we'll hit return and we have the same answer. So MATLAB has a fairly flexible syntax, and this can be convenient because it means that you don't have to be too careful when you're writing code, and old code will remain compatible if they change the syntax needs slightly. But by the same token, it can be slightly confusing at first that there can apparently be a lack of consistency about what is needed or not needed when you write a program or you write a single command like this. But anyway, so what we've got here is we have defined a matrix A 2 by 2 matrix, and let's do something with it. Well, one thing about matrices is when we multiply them together, we can multiply them by using the star operator. So we'll do A star A and see what that does. And if you look closely, you will see that that answer that comes out is the result of doing a matrix multiplication rather than multiplying each element in the first term of A, the left-hand A, and multiplying with each element of the right-hand A. So when I do A star A, MATLAB does a matrix operation, and this should be considered to be quite distinct from other programming languages which do an element by element multiplication. So to get an element by element multiplication, we use our dot operator again. So we do A dot star A and we hit return, and you will see this is what we would expect if MATLAB was doing was iterating the multiply function over each and every one of those elements in the 2 by 2 array. So we can think of that variable A as being either a 2 by 2 matrix, on which I can do matrix-like operations, or I can think of it as a 2 by 2 array. And of course, in programming terms, there's no real difference between those two things. It's a question of how we think about it. But we do need to be careful to make sure that when we're using a star operator on a multi-dimensional array, that we are doing what we think we're doing. And the golden rule with all of this, as it is with any part of programming, is to test your code, and preferably to test little pieces of it, to see that things are working as you expect them to, before you then trust a larger calculation that uses some small piece of code like this. So let's look at some other matrix operations that we can do. Well, of course we can define larger matrices. Let's define a 3 by 3 matrix. So we'll do B equals, and let's do some random numbers this time. And I'm going to omit the commas because I can. And okay, this is just the same as before. And we can do B star B, and that will work, of course. But of course, A star B doesn't work because, of course, it's trying to do a matrix multiplication, and these matrices are of different size. Let's define another array C. I will do C, and I'm going to do C is equal to 3, 4, 5. So this is a 3 by 1 element array. So I define that. And let's see what happens when I do C star B. Aha, it's done a matrix multiplication, and B star C doesn't work. So why is that? Well, if you consider that B is a 3 by 3 matrix, you can now consider that C is a row vector. So when I try to multiply B onto C, you can see that because C is a row vector, it is pointing the wrong way. That when I multiply element by element along the first row of matrix B, it will only encounter a single column in vector C, and therefore it doesn't have enough elements to do a proper calculation. What I should really do is redefine C, if I want this to work, as being 3 semicolon 4 semicolon 5, and that defines C as a column vector, and now when I do B star C, it does work, and it does what I would expect it to, which is a matrix operation on a vector to yield another vector. Now sometimes this can be quite confusing, and it can be compounded a little bit because of course I can transform vectors from one form to another form. So let's define C as a row vector again, 3, 4, 5. One way to transform that row vector into a column vector is to do a transpose. So I'll do C transpose, and now it's a column vector. So if I do B star C transpose, it will work as it did before. But it won't have changed C from a row vector into a column vector as part of that operation. Now that works as we would hope it would, but let's try something a little different. I'm going to create another vector D, and I'm going to make that into a row vector as well. So I'm going to call that 6, 7, 8. And just remind myself what C looks like. That's another row vector. So really, when I do a dot product of those two, it shouldn't work because one of them is a row vector and one of them should be a column vector and isn't. It's also a row vector. Let's find out what the operation for a dot product is. Well, we're not quite sure, so we'll do help dot. Hope that might be the right thing. And it is a vector dot product, so if we try dot C comma D, and it does work. It provides us with a single value, as it should do if we're assuming that those two objects are supposed to be dot products together element by element. So the dot product function is conveniently forgetting that actually one of them is not the right way around. And if I do dot D comma C, it should give me the same answer. So irrespective of whether those two vectors in the dot product arguments are row vectors or column vectors, in other words whether or not they have semicolons or not, doesn't really seem to matter. And we can test to see if that's true by dotting C with D primed, so explicitly taking the transpose, and it makes no difference at all. So MATLAB is a little bit flexible again, or what you might say is inconsistent. And the golden rule again here is to test things and check what's going on as you write code. So that's some of the basic matrix operations. But some of the other things I might like to do with arrays is to grab pieces of them and do operations on those. So let's look at how that works. Let's create another array. I'm going to call this array X this time, and I'm going to make it a set of sort of semi-random numbers. How many have I got there? I've got 8 of them. So I've now defined that array X, or a row vector X if you like, and I want to extract out the fourth element of that array. Well, the way to do that is to use the normal bracket notation, and to extract out the fourth element I do x4 and I get the value 6, and of course I can do this for any of the other array elements. I can get the third element, I can get the 7th element, and so on. The thing to remember about array indexing is that I'm not restricted to just using single numbers. I can use any set of numbers which are generated by any other expression. So for example, if I want to extract out the 2nd, 3rd and 4th elements, I can do this by doing x, and let's just close the brackets as to indicate that I'm trying to find some elements of x, and I'll go back inside those brackets and I'm going to create an array I want to get the second, third, and fourth elements. And when I hit return, you can see I get the values 3, 4, and 6 from the original array X. So that's good. But maybe I want to do that in a slightly more convenient way. Say if I had very many elements that I wish to extract from an array. Let's try doing X, and instead of creating an explicit array, I'm going to do 2 colon 4. So I'm going to create a list of elements, an array of element numbers, 2, 3, and 4, by using that colon notation, and I get the same answer again. So of course this is quite powerful because it doesn't restrict me to contiguous, in other words, successive elements of an array. I can extract any elements I like. For example, if I wish to extract out all the odd elements of that array, I could do that quite easily by doing x1 colon 2 colon, how many elements do I have in my array? Well, let's say up to 8, because I happen to know that my array, in this case, has a length of 8. It has 8 elements inside it. So if I start from element number 1 and go in steps of 2, using this colon notation, I will extract out the odd numbered elements. In other words, the elements that appear in the odd positions of the array X. And I'll just show you the original array so that you can see that's true. And of course I can do the same thing for the even numbered elements simply by changing that 1 into a 2. But sometimes I have a very large number of elements in my array, and I may or not even know how many elements I have. So let's create a larger array. I'll recreate X, and I'll create a very large number of single-digit numbers. And I haven't counted how many I've got. So let's find out how many I've got. Let's try length of A. Does that work? Length of X, sorry. Is that a function that exists in MATLAB? Yes, it is. So if we do help length. So all I've done is I'm not very good at remembering the various function names that exist in different programming languages because they're all quite similar and yet slightly different. So it's very easy to forget which function name goes with which programming language. My advice, which is what I do myself, is I make a guess, and if it's not correct, then I'll have a hunt around in the help until I can find it. But always remembering that because MATLAB was written for doing scientific programming, it should be expected that within the MATLAB system somewhere there should be some function that does the kind of thing you want in a reasonably compact form. Okay, so let's see is there a function called size? Maybe there is. We'll do help size, see if that exists. Size does something, which is the size of an array. So so length gives me the length of a vector, whereas size gives me the size of an array. So let's have a look at what size of X gives me. The size of X is telling me that it's a one-dimensional array with 18 elements. So I guess that if I were to do size of X transpose, it would be the other way round. Okay, so length of X tells me how many elements I've got in that array, whereas size of X tells me that it's a 1 by 18 array. So if I want to extract out the odd elements of that array, I can now do that quite conveniently by doing X, and if I didn't happen to know how long the array was beforehand, I can do 1 colon 2 colon length, type that correctly, length of X. So I can interrogate the array X, find its length as part of that expression here that I'm using to construct which elements of X I wish to extract. So I hit that, and now I have the odd elements. It's an interesting question to ask oneself. Can I just enter in any number? Can I enter in 100? Will that work? No, it doesn't. So sometimes MATLAB functions will be tolerant of you requesting things that are going outside various boundaries. But when it comes to arrays, you can see that you can't ask for an element of an array that doesn't exist. So you do need to use that length X notation. As so, where did it disappear to? It was, yes, it was 1, 2, and then it was length X, like so. Okay. Now, let's have a look at multidimensional arrays. Let's go back to our matrix A, which was a 2 by 2 matrix. what is the length of A? Well, the length of A is 2, which is perhaps a little surprising. It might have been 4, for example. So if I have a multi-dimensional array, or a matrix, then we have to be a little bit careful about our interpretation of what the length function gives us. But the size of A is at least fairly unambiguous. It tells us what's going on. So we'll look back at that matrix A again. This is where things can get a little bit confusing, because let's say I want to extract out the top right element of that matrix A. Well, we might expect that that would be A1, 2 now. Okay, perhaps I should have chosen a slightly different number. Let's redefine A, so we'll call it 5, 7, semicolon 4, 3. Try that. And if I do the top right element, which is the first row and the second column, then it returns 7, as I would expect. So that's all fine. I need to use a comma to indicate the first row and then the first row and the second column. So the first element of that designation there, it tells me which row, and the second element tells me which column. But I can also do A2, which will return something else. Aha. So I was expecting that to give me 7, but I forgot, as is easy to do in this syntax, that actually MATLAB goes down the columns first and then goes from column to column. So the second element of A is 4 and the third element of A is 7, which can be a little bit confusing. Let's try that on a slightly larger matrix. Here's our 3 by 3 matrix. So before we had B, 1, 2. Let's see what that should give us. No prizes for guessing that. Should give us the number 3. Let's see what B3 gives us. That gives us 7. So if I ask for the 8th element of B, it should give me 3, right? Which is, in other words, is this one here. Okay. Now, just as with single-dimensional arrays, I can extract out sections of a large matrix using the colon notation. And let's try that. So we'll type B. I want to go from the first row to the second row. Try that, see what happens there. And from the second column to the third column. Or is that what's going to happen? Let's see what happens. So it's going from the... Yes, it's doing the first and second rows and the second and third. First, second rows and second and third columns. In other words, it's extracting out this top right section. So that can be a little bit confusing, as you can no doubt hear in my own voice. So if you wish to extract out some subsection of a larger matrix, you can do it that way, although that can be a little bit cumbersome. Let's say we want to extract out the first row only. Is there a simpler way to do that than typing something like I want to extract out the first row only? I would probably want to do B and then comma 1 colon and, well, in this case I know it's 3, so that should give me the first row of that matrix. But it might be a little bit difficult to extract out from the size command which one of those dimensions I wish to use. But maybe if I did B bracket 1 comma, and I'll do 1 to size of B. Will that work? Because size of B is going to give me 2 things, isn't it? So really what I want to do is I want to extract out that first element of size B. That's not going to work very easily. So let's try something a little simpler. I'm going to just put a colon in, and it gives me 2, 3, 1. So a single colon, highlighted there, allows me to extract out all the elements for this row, and that's a much simpler way, which avoids having lots of complicated syntax. Similarly, I can extract out, say, the second column by extracting out all the elements which are in the second column. And there they are. If I just bring up B again for reference so you can see that's true. So array indexing is very powerful, but I have to be a little bit careful when I'm using it. Now what about defining large arrays? Are there simple ways of doing that? Well, we've already seen that we can define a large array of consecutive numbers, say x equals 1, 2, 3, 4, 5, and so on. I can convert that into something which is a bit more compact by using something like this, a colon notation. So say I want to generate a set of integers from 1 to 100, I can do that very simply using that notation. But let's say I want to do something, I want to create 100 values which are all a certain number, say 5. Is there a way of doing this? Well, let me show you a few tricks. There's actually more than one way of doing this. One easy way to do that, which is a little bit of a hack, but bear with me. We'll take that array x that we've just defined, which are the numbers 1 to 100, and what we can do is we can multiply 0 times x, and that will generate a set of zeros. And if I want to create an array of 5s, I can do 5 plus 0 times x. There we are. So now I've created an array which is a set of 5s. But that's slightly cumbersome, and it's also a little bit misleading, because when you see that expression, which I'll just bring up here, so let's just put it, so we could write it without having to define the array by doing this. I could write, please generate the numbers from 1 to 100, multiply them by 0 to make a set of zeros, and then add 5 to them. And that will generate a set of 5s. Oh, that hasn't worked, has it? Because I haven't put the brackets in the right place. You can see there is some kind of operator precedence, as it's called. Perhaps what I should do is put brackets around that, and now it works. Okay, so you have to be a little bit careful with your operator precedence, as it's called, to make sure that things are being added and multiplied and generated in arrays in the right form as you expect them to be. In fact, that's generally true, of course, in any programming language. So you can see that's a slightly cumbersome way of doing it. 5 plus 0 times the number from 1 to 100. And it's also a bad way to do it because it's misleading. It indicates to the reader of your code, remember that in the future when you write code you might be having your code reused by somebody else, and they'll want to know what it was you were intending to do. And you may also look back at your own code and think, what was I meaning when I wrote this code? So doing a hack like this certainly works, but it's not recommended. Is there a simpler way of doing it? Well, maybe there's a function that will generate ones and zeros. And let's see if there is. I'll type here, help ones. Is there such a function? Well, it's been highlighted in pink in my workspace there. And you can see, yes, ones creates an array of ones. But if I type ones 4, remember that MATLAB means matrix laboratory, so we will create a 4 by 4 array. So if I want to generate a 1 by n array, a 1 by 4 array, for example, of ones, I can do it by giving 2 arguments to that function instead of 1. If you look up at the help, you'll see that I can call the ones function either with a single argument, which creates an n by n matrix of ones, or I can call it with 2 arguments, which will give me an m by n size matrix, where I can either make the m equal to 1, or I can make the n equal to 1. And of course I can increase the number of arguments. And this is quite common, that functions can take a number of different arguments, and they can also return a number of different results, depending on how you call them. So you need to be a little bit careful of that. We'll look again at that a bit later on. So I've created my matrix of ones, and in this case a 1 by 4 matrix, in other words a simple one-dimensional array, and I can now do 5 plus ones of 1, 4. That hasn't done quite what I wanted to do. I should really do 5 times ones, shouldn't I? Okay, 5 times ones, and in fact I want to generate 100 of those numbers as I originally wanted to. You can see that's how I can do it. And that's probably the best way to do it. That's the least ambiguous way, the way that indicates most clearly that you're trying to generate a set of 5s rather than doing anything else. Another way I can do it is I can call a function called zeros. And is it with an e or without an e? We'll find out in a minute. Let's add a plus to it. Yes, that seems to work. So zeros generates an array of zeros. Let's see that without the 5 added to it, so you can see how that looks. So zeros is another function that does much the same. So I have these sort of helper functions called ones and zeros that allows me to fairly conveniently generate a set of matrices or arrays as I would like to for various purposes, and we will see why that's useful in a later video.